Alright, let's start from the basics. SHAP stands for Shapley Additive Explanations, and the idea comes from cooperative game theory, and the goal is to break down a model's prediction into contributions from each feature. In other words, it tells us how much each feature pushed the prediction away from some baseline value. Okay, now to make this work, SHAP follows four main principles. What are they? First, efficiency. The contributions of all features together should add up exactly to the prediction minus the baseline. Second, symmetry. If two features contribute equally, they should get an equal credit. Third, the dummy principle. If a feature has no effect, it should get 0. And fourth, additivity. Explanations should stay consistent when we combine models. And why do we even care about SHAP? Because it helps us with transparency and trust in the model, which is important when people need to understand decisions. And it also supports compliance with regulations. It helps us debug models and gives us insights into which features matter the most. And when we think about real-world use, SHAP is applied in healthcare, credit scoring, marketing, and research. Okay, and theory is here. In game theory, Shapley values are a way of splitting the payout of a coalition fairly among players, depending on how much each one contributes. The definition looks a bit intimidating, but here is the pi sub I equals the sum over all subsets as not containing I of the term. Okay, open parenthesis, absolute value of s factorial times open parenthesis n minus absolute value of s minus 1 factorial close parenthesis divided by n factorial close parenthesis multiplied by the margin contribution, which is v of s union I minus v of s. And that formula basically says we look at all the possible ways features can form groups, then measure how much a feature adds when it joins the group, and then average it out with fair weights. In machine learning terms, we treat features as players, and the model output is the value function. The SHAP form looks much simpler. You can see here f of x equals phi 0 plus the sum of phi I. So the prediction is equal to a baseline plus the sum of feature attributions. And so how do we actually compute these values in practice? That's where SHAP methods come in. The two main ones are the tree SHAP and kernel SHAP. Tree SHAP works specifically with tree-based models like gradient boosting or random forests. It is efficient, runs in a polynomial time, and gives exact results. And kernel SHAP, on the other hand, is model agnostic. It works with any model, but it's based on sampling, so it's slower and approximate. If we compare them side by side, tree SHAP is fast and exact, but only for trees. Kernel SHAP is slower, approximate, but it works with anything. And here's we have an example. So what is that? Suppose our baseline value is $300,000. For house 1, the prediction came out to 350,000, while actual price is 315,000. That leaves a residual of minus 35,000. If we break it down by features, the size of the house had a SHAP value of negative 15,000, meaning it pushed the prediction down. Okay, the location score added some positive contribution, the age also added, and then we have the unexplained part, which balances things so the sum lines up with the actual. So what is the point here? With SHAP, we can say not just what the model predicted, but also why. The base value plus each feature's SHAP gives a prediction, and if it doesn't perfectly match the actual, that difference is just a residual. And okay, you can see other examples. House 2 here and house 3 here. House 4 and finally house 5. Okay, and that's okay. When it comes to interpretation, SHAP can work locally or globally. Local explanations help us understand individual predictions. For example, why was a loan denied? Why did the model flag fraud? Why was a medical case treated a certain way? Global insights look at the bigger picture. We aggregate SHAP values across the dataset to find overall feature importance, interactions, and model behavior patterns. Okay, and there are also some best practice we should follow. We should validate explanations with domain experts because numbers alone don't always make sense. We need to consider correlations between features. Choosing the right baseline matters a lot. We should check if explanations stay stable across different runs. Maybe combine SHAP with other explanation methods, and always document the interpretation process. And final part, real world applications. And here in healthcare, SHAP helps with clinical decision support, drug discovery, and even medical image analysis. In finance, it supports credit scoring, loan approvals, fraud detection, and regulatory compliance. And here in marketing, it's used for churn prediction, recommendations, pricing, and analyzing A/B test results. And in research, it supports climate modeling, genomics, material science, and social studies. And the bigger picture, SHAP has become a cornerstone for explainable AI, and it helps organizations build trust by making decisions understandable. It helps them meet compliance requirements by showing transparency, and it supports innovation by pointing out patterns and insights that may not have been obvious before. So that's the follow. We started with what SHAP is. So the game theory foundation looked at methods, tested it with a house price model, and then moved into interpretation and real world use. That's for this lesson, and thank you for listening.